Hello everyone, and welcome to my presentation for the AMU Final Hackathon. Today I will be walking you through my machine learning pipeline designed to predict home credit default risk. My primary objective was not simply to maximize accuracy, but to engineering a model firmly rooted in the principles of responsible AI. Throughout this presentation, I will detail how I built a robust classifier while actively ensuring fairness, mitigating bias, and providing crystal clear interoperability. Before we evaluate fairness, we must ensure our foundational model is technically sound and robust. The home credit dataset presents a massive challenge: extreme class imbalance, where approximately 92% of the applicants belong to the Navigate class, meaning they successfully repaid their loans. To handle this, I engineered a domain-specific financial features such as the credit-to-income ratio and the annuity-to-income ratio, which provides the model with logic behavior indicators rather than just raw numbers. For the modeling algorithm, I selected LightGBM, configured with balanced class with to heavily penalize the model for missing potential defaults. Crucially, to validate performance without data leakage or skewed results, I implement a five-fold stratified cross-validation strategy. Relying on simple accuracy here would be highly misleading. Therefore, I optimized and evaluated the model using ROC-AUC as the primary matrix and PRAUC average privation as the second matrix. Ensure that our baseline model is mathematically reliable before we adjust for effects. This brings us to the first major focus of the promote, RAI principles and fairness. Machine learning models are pattern recognition engines. If historical data contains systematic bias against a certain demographics, a naive model will quickly learn and amplify this bias. To prevent this, accountability and fairness check must be explicitly coded into the pipeline. In this notebook, I conduct a rigorous fairness assessment focusing on gender as a protected attribute. I evaluated two strict fairness criteria. First, demographic parity. I analyzed the overall prediction rises to see if the one gender was being disproportionalities flagged for DNA regardless of their actual credit worthiness. Second, and more importantly, I measured the equalized odds, which look at both the true positive rate and the false positive rate across the groups. In a lending context, equalized odds asks, among the people who actually defaulted, did the model detect them at the same rate across demographics? And conversely, among those who repaid, were they falsely flagged at the same rate? And if we detected a significant divergence in these rates, for example, if the false positive rate is 5% higher for one demographic, it indicates that the model is unfairly penalized this group. To address this bias, my pipeline proposes a specific mitigation step, threshold tweaking. Rather than discarding the model or altering the ground truth data, we can adjust the decision thresholds diametrically in production by setting a slightly different probability cutoff for marginalized group, we can mathematically align the equalized odds. The ensures equitable credit access while still effectively managing the bank's financial risk. This proactive approach transitions RAI from a theoretical concept into a deployed engineering practice. So moving to the second promote, improving model interoperability. Tree-based concept models like DightJVM are incredibly powerful, but they operate as black boxes. If we cannot explain how a model makes its decisions, we cannot trust it. And we certainly cannot use it exactly in consumer finance. To break open this black box, I integrated several advanced expandable AI techniques. First, to understand the model's Markov-level behavior, I generated partial dependence plots, or PDPs, and sharp global summary plots. The PDP allowed me to isolate specific engineering features like the credit to income ratio. And to prove that as an applicant's financial burden increases, their predicted risk default smoothly and logically increased as well. The sharp global summary plot revolved the overall heuristic of our data. It shows that extremely credit bearish scores specifically X-SOS2 were the strongest drivers of the model's predictions. The global interoperability provides to stakeholders that the algorithm is making decisions based on limited financial indicators, not separate correlations. And however, global expansionality is not enough to support exact decision-making on an individual level. If an applicant is denied a mortgage, handling them a global feature importance chart is entirely unhelpful. They need to know why the specific application was rejected. To solve this, I implemented local sharp explanations using waterfall plots. As you can see in the screen, for machine learning uh, counterfactuals for their prediction, it starts at the baseline average risk, and they map out exactly how much each specific features, perhaps their age, their specific income level, or their employment history, pushed their risk score up or down. This local interoperability is a cornerstone of the ASIC AI. It provides actionable results. Instead of a lone officer saying the computer declined your application, they can look at this plot and see you were declined because your annuity to income ratio is were declined because its ratio is uh, 12% above our acceptable threshold. If you pay down this specific debate, your score will improve. It ensures transparency, empowers the consumer, and keeps human oversight firmly in the loop. Finally, the model is only used it can be safely deployed. In the final section of my notebook, I outline the protection readiness considerations. I discarded the default 0.5 decision threshold, which is an attribute and rarely optimal for imbalance data. Instead, the pipeline dynamically calculates the exact threshold, in this case, around 0.5013 that maximize the F1 score, perfectly balancing precision and recall for business needs. I also isolated the data processing and featured engineering steps into a single callable function. This ensures that when live real-time JSON requests come into the banking API, they are processed with the exact some logic using during training, preventing data leakage. Lastly, implemented post-deployment monitoring for data drift, especially targeting the top sharp features like ext-source2. So the engineering team is instantly alerted if the real-world data distribution changes and the model requires retraining. In conclusion, by embedding rigorous cross validation, algorithmic fairness checks, and granular interoperability directly into the code, this project demonstrated that highly accurate, predictive analytics, and responsible AI are not mutually exclusive. They are complementary necessity for modern financial techniques. Thank you.